Okay, so good morning, everybody, and welcome to the lecture about fatigue crack growth simulation by extended finite element method. My name is Aleksandar Grbovic, and I'm coming from the University of Belgrade, from Department of for Aeronautics, as you can see. My colleague, Professor Sedmak, will join us. I mean, he's a little bit late. Okay, so just to tell you a few things about myself and about my investigations. Basically, I'm a designer of the airplanes, and my job at the University of Belgrade is to teach students how to design aircraft, how to, do all these calculations. And my, let's say, main or narrow area of interest is fatigue design of these structures. So this is summer school, and I just want to show you some of the things that we did, some problems that we solved for the customer. So all these here case studies that you're going to see today are from reality. I mean, from real life and from the problems that occur in aircraft and aerospace design. But you know, as a professor, I also have to tell you something about some basic theoretical approach here and what is behind all these calculations that you're going to see today. And you know, fractures due to dynamic loads, so they are occurring since ancient times. And here, because we are in this beautiful country of Croatia, so I just wanted to mention that one of the biggest or greatest scientists from Croatia, and his name is Ruggero Giuseppe Bošković, maybe you heard about him. So he also tried to solve some problems with the cracks in, as you can see, 16th century. And at the order of the Pope Benedict XIV, he made two experts reports about the cracks on the dome of the Basilica of St. Peter. Of course, we don't know. I mean, I didn't see that those reports, especially because they are written in Latin. But we can see that crack growth and crack appearance in different structures is a very old problem. But we started to analyze and to deal with this kind of the problem when metals became the dominant material in the construction of the structure, which means 19th and 20th century. So when we talk about material fatigue, we can say that fatigue is the weakening of the material caused by cycle loading. And as a result of this cycle loading, after some time, material becomes weaker and then crack starts to grow. And our goal is to prevent this, or if crack appears, we must know how to deal with these cracks. So again, I'm talking here from the point of view of the engineer who is dealing with this every day in his practice. You can see here some of the examples of the material fatigue. So this jackhammer component, as you can see here, shows no yielding, but before fracture. But when we look at the cross-sectional area of this jackhammer component, we can see here where is the crack initiation site. For some reason, this laser is not working. Okay, never mind. So this crack initiation site is here, as you can see. Then we can see these striations as crack grows. Okay, so it makes some damage to material until final fracture, and this fracture zone is in this area here. So it's very easy to recognize when fracture is caused by crack growth. And one of the reasons why I'm showing you this, you will see later that we can simulate this kind of phenomena using finite element method and extended finite element method. Okay, so in design of structures, and today we'll see all of my examples will be from design of aircraft structure. We have two approaches or two philosophies. Number one is so-called safe life approach. And in this kind of approach, we don't allow any kind of crack to appear in the structure. This means that we have to predict the time when damage will occur and replace the component the structure before that damage occurs. In the case of aircraft design, landing gear, wing fuselage attachments, engine mounts, they have to be designed so that crack never appears. Unfortunately, these cracks are, little devils, and from time to time they appear. The newest example, a couple of days ago, 4 or 5 days, I read in newspapers, so there is a problem with the Boeing 777 aircraft. So they had 3 test sites, and on all 3 test sites, they discovered, I'm talking about the aircraft which is still not in the use, okay, so it's still in the development phase. And now they're testing these 3 pieces. So they discovered cracks on the thrust links. What is thrust link? Thrust link is the part of the aircraft which connects the wing with the engine. So if damage occurs on this kind of component, very soon you will lose your engine. And they found cracks on all 3 links during testing phase. So this means that probably there is a problem with design. You know that nowadays we are trying to make structures to be lighter, to be, cheaper. And very often we use, nowadays we also use 3D printing. Okay, in this case, these elements are not 3D printed. But, all these efforts that we are put on nowadays, we just want to make cheaper, lighter, so they can move faster. And then the problems, as you can see, occur. So that is the engine mount that you can see on this slide. So that's the part of the engine mount. The other approach is called fail-safe concept. In this case, we allow cracks to appear. Okay, why? Because we have redundant structure. In the case of aircraft, for example, cracks can appear on wings or the fuselage or engine cover. Why? Because wing, for example, it has many parts, many components, and very often these components are like in tens or hundreds of pieces, okay? And if one fails, then the other components will take the load from that failed one. And don't be afraid if you're, a frequent flyer or not a frequent flyer. If you see some cracks on the wings, on the fuselage, okay, it's safe. But we have to, follow the crack growth of that crack, the speed of rate of growth, and eventually we have to do something, either to replace that component with a spare part, or to make some patches and then stop there. So we will see some of these efforts a little bit later. Okay, so this is the example of bad fail. A bad fail-safe design. So this is the Hawaii Aloha Flight 243 Boeing 737 accident that occurred, I think, in 1995 or 1996. I'm not sure. Where you can see that during the flight, this aircraft became something like convertible car. As you can see, this is also very important why to put your seat belts on, even if you are on the, let's say, cruising altitude, okay? Because the guys who didn't use that didn't survive, okay? But of course, we don't want to see this. We don't want to experience this, okay? Because it's really bad thing. Lives here are in jeopardy. And I think here 5 or 6 people die. But this kind of accident happened when I was a student of the last year at my university, approximately, or maybe I was a PhD student, I really can't remember. And one of my first efforts to simulate this kind of thing was inspired by this accident. And on this next slide, you will see the explanation what happened here in this case of Boeing 737. So you can see here these holes, we call them rivet holes, because most of the connections on the aircraft are riveted connections, which means we drill a hole and we use a rivet to connect, let's say, one plate of the skin of the aircraft with another plate of the skin. And of course, these holes, we call them stress concentrator because stress usually is very high in the area around the holes. So here you can see 11 holes, and here I simulated 22 cracks growing simultaneously. So 11 holes and 2 cracks on each side of the hole. And you can see what happens here. Cracks, they grow, and eventually they become one crack, one big crack, and then that big crack will grow without any control. This is the example, why I use this example, particularly this example, because in NASA during in the 80s or 90s, in the last century, they tested this kind of panels with these holes, and I had results from these testing, so I could compare my results with results from NASA. But basically, this is what happened on Aloha 737. Several different cracks started to grow independently, and eventually they joined and made one huge crack, which ripped off the part of the fuselage. You saw that on a screen. So the goal of all these simulations and all these efforts in numerical modeling is to avoid this, okay? Or to predict at least when this will happen, and then to do some corrective actions or replace the whole part. Okay, when we talk about crack growth, we have, in fact, two stages or phases. Phase number one is called crack initiation period. During the crack initiation period here, you can see we have cyclic slip, crack nucleation, micro crack growth. And here, in this period, we talk from the theoretical point of view, we analyze stress concentration factor, KT. The second phase or second stage is a crack growth period. Now crack is visible because mostly this happens inside the material, we cannot see that. But once crack becomes visible, then we have this macro crack growth until final failure. And here, the most important factor for analysis is called stress intensity factor. Probably you know all these things. But okay, my job is to make some kind of introduction to you. So don't worry, it will not take a long time. So stress intensity factor, SIF, is used for predictions on crack growth, and you will see later through examples how we calculate stress intensity factor. Okay, when we talk about crack growth, we can identify three regions, or again, three phases. Phase number one is crack initiation. This is yellow here in this image. And this is region where delta K is less than delta K threshold. Why delta K? Let me remind you that fatigue is caused by dynamic loads, and these dynamic loads are changing over time, and we can identify the maximum and minimum load. And then we talk about range of the stress. We can calculate the stress intensity factor for the maximum value and for minimum value, and then we talk about range. So we discovered that range is, in fact, the most influential when you talk about crack growth. So the second phase is where we have a stable, for some reason this sometimes lazy is working, sometimes not. Okay, never mind. So in the second here phase or stage, we have more or less stable crack growth, which means that rate of crack growth is more or less constant. And you can see here on this logarithmic diagram, we can here find the slope of this because it's almost straight line in this graph. And finally, phase number three is when we have a crack growth which is not controlled or uncontrolled. So this is what we want to avoid. And basically, in a crack growth analysis, we focus on this phase number two. And for phase number two, it's also called, as you can see here, Paris region. Why? Because this is named after the guy who described and derived the formula for this. And you can see Paris equation on the top of the screen. But over the time, other scientists like Foreman or Walker, they proposed another formulae, which are more or less the same as Paris formula, but with some improvements. Okay, so they included more factors to analyze this. You can see here the meaning of all these factors, but maybe the most important formula nowadays for crack growth evaluation is called Nasdaq equation. Again, this formula is coming from NASA laboratories. So during 60s and 70s, when Apollo program was very important for American, not only scientific communion, but also for American country, I mean, for People of America, so they worked on hundreds or maybe thousands different specimens, trying to evaluate these coefficients for different materials. So they came up with a database, which is called NASGRO database. And in that database, you have, like, let's say more than 400 different materials. And you can see that this formula is a little bit more complicated than Paris or Walker equation, because now I have to evaluate something like 10 different coefficients. But the good news is that this database was, I have good news and bad news. This database was available for free download until 2004. So you could go to the NASA website, download the database, and use these coefficients without any charge. But in the last 20 years, they ask you to pay the money for this. And in the last 20 years, they improved the database. They have more and more materials every new version of the software. Good news is also that I have the database from 2004, and occasionally I use the coefficients from this database. NASGRO equation is something that I'm using in my calculations in the last, let's say, 10 to 15 years. Okay, and all these coefficients like CP, QN, are empirically obtained, as you can see, but you will see something about this more later. Yeah, so specimens used in a fatigue life evaluation. For example, compact adhesion is the most widely used type of the specimen for fatigue analysis. Also, this CCT, central crack tension, is used. And these specimens are also important because for them we have analytical solution for stress intensity factors, which means that we can compare our numerical approaches with results obtained from analytical solution, which is also very important for validation of your model. Okay, stress intensity factor, how we calculate this. I'm not going to waste my time here on this one because this is pure theoretical thing, okay? Here you can find some of the sources I used here to put this formula on, like this TOFAT, stress intensity factors, weight functions from 2008. What we can see here, these formulas are very complex. They involve many different parameters, and it takes time to use them if you want to use an analytical approach. But by the time when I was finishing my studies, okay, like 30 years ago, this was the only approach we could use, because numerical approach was, invented, of course, but we didn't have powerful computers to carry out these calculations. Just one simple example. When I bought my first laptop in 1998, let's say, I couldn't run a finite element model bigger than 300,000 nodes. So simply didn't have enough memory, didn't have enough CPU power to do that. My newest laptop that I bought last year can run more than 5 million nodes. So and just imagine in the 80s or 70s, what was the computational power. So analytical approach was the only approach, with some, of course, adjustments using some coefficients. You multiply result by some coefficient in order to evaluate something. So that was the approach. But with numerical approach, we can easily handle these formulae. You program them once, you write your own code, and then you can run as much simulations as you want. And the best thing is all these here equations. Look, this is what? This is CCT specimen. This is the crack in the middle of the specimen. And then these are solutions for displacement of the crack surface and stress field, sigma 2 around the crack tip, okay? And this is only for this kind of problem when you have, CCT specimen. If you have structure, which is complex, with complex geometry, this formula for you is more or less useless, because this formula can be applied only in a case when you have crack in the middle of the plate, okay? So this is why numerical methods are very important nowadays, because using some of these software here, we can evaluate the crack growth, number of cycles that will lead to the final damage. And I use them all. in the last 30 years. NASGRO, Frank 2D, this is short for fracture analysis code developed by Cornell University in the United States. Then fracture analysis code for 3D analysis. Then ANSYS, probably heard about this software. MSc Fatigue, Abacus, also very popular among students. Codestair and Zebulon. So they all have code written for analysis of the fractures and crack growth. Okay, of course, it's all, finite element method, of course, except these last three, which is called extended finite element method, which was something very special and very new 15 years ago. But today, let's say, almost commonly used. Okay, my students are using extended finite element for their master thesis, not for PhD. But 15 years ago, it was a big deal. You know, how to apply this code, how to solve the problems using extended finite element method. Okay, let's start with NASGRO. So that was, this is that software that was available for free download. Now it's not. And this is how it looks like. Okay, so you have this basic first screen, unit selection, you pick from the database your type of the specimen. In this case, this is a specimen with a hole in the middle. And then you define here some dimensions, you define the load. Then next step, you choose material. In this case, my choice was aluminum 2024 T3, because this is the most widely used material in aircraft design. And you can see here all coefficients for NASGRO equation, C and P, Q, D, K1, B, K, A, K, K1, C, and so on. And then you simply implement this in your calculations, okay? And next step in NASGRO software is this. You get, again, this was used like 25 or more years ago, okay? And then this is the result. So NASGRO gives you values of stress intensity factors along with the crack length. And here in this case, you can see plate thickness, plate width, hole diameter, and so all these geometrical dimensions. And then you get something like this. And another output is this. You get a number of cycles and here crack growth. So you can see, and then you can analyze here. And also here we can see in this graph, we can see the period of the stable growth, right? And then we can see period of very fast growth, which leads to final damage. So this is what we used 25, 30 years ago. And this was like cutting edge technology at that time, okay? And so it was very useful. Why I've chosen this hole in the middle? Because of these rivets, okay? So rivets are holes in the middle of some structure. But you could also here select CCT specimen, CT specimen. So you have, and it's based on, I forgot to say that it's based on boundary element method in this code within NASGRO version 4. Frank 2D or fracture analysis code 2D. Again, this is my work from 25 years ago. So I went to the website of the Cornell University. They allowed me to use this software for testing purposes. And then I simulated crack growth using, as you can see, finite element method. So this was one of my first efforts in a field of fracture analysis using finite element approach. So this is 2D model. And then you can see here, I define the crack tip here. And then you can see crack growth through this structure. And also you can see that around the hole, I made a denser finite element mesh in order to get more accurate results. And this is basically one of the most important rules, okay? So if you want to get better results, more accurate results, you should use more nodes and you should use more here elements in order to get better solution. Of course, I compared my solution from Frank 2D with NASGRO results. Also, you can see here I use two types of the elements, triangular elements and quadrilateral elements with 8 nodes, and this with 6 nodes. And you can see comparison of the K1 values So stress intensity factor value for mode 1. And you can see very good agreement between the values provided by NASGRO and Frank 2D software, either by using automatic crack growth or manual crack growth. In manual crack growth, you have to define the mesh after every step of the crack growth, because you get new geometry, new structure, because it's damaged. The damage is growing, and then your geometry is every time new, and then you have to define new. So this was very painful job, trust me, because at that time, I mean, computer and software was not user-friendly. Okay, so you had to do all these things manually by typing some coordinates in a notepad, and so on and so on. Nowadays, it's much easier. But this, I was very happy when I got results like this. I compared them to NASGRO, and I was very happy about it. Okay, what was next step? Now, when I have this, change of stress intensity factor where the crack length, then I define polynomial equation of this line, and then I go and integrate NASGRO equation using this polynomial line. So this was the only way to get the number of cycles. Of course, NASGRO is doing that automatically, but in Frank 2D, I didn't have that option. So I had to do this by myself to integrate this NASGRO equation and get the number of cycles. Again, I compared that to the results from NASGRO and got very good agreement. Then fracture analysis code 3D came. In this case, you could, as you can see, analyze 3D structures. This is, by the way, a dental implant. So now if you ask yourself, so what the hell is aircraft engineer has to do with the dental implants? Okay, also these implants were, started in the early, 21st century. And so these doctors, dentists, they came to my department asking who can help them. So they heard something about some new method, finite element method. What's that? It's new, it's cutting edge. And then I worked on several the different projects. And for me, this was also very good thing, because we had a, let's say, solid base for investigation, experimental and numerical. So this was 3D implant and crack growth in a 3D implant. And you could get values of stress intensity factor along the crack front, because in the previous example with 2D, we have only one crack tip. It's just one point. But here in 3D analysis, we had the crack front, which means we have many nodes on the crack front. So it's like you can see on previous slide, here I use penny-shaped crack. And then maybe it's not visible, but here you can see the generation of new crack fronts after calculation. And then this is how, again, step by step, we grew the crack and then calculate the shifts for every step of growth. And these are values that you can get with NASGRO. You see K1, K2, K3, so NASGRO, sorry, from Frank 3D. And also you can find the values of J integral here, kink angle. And you can see here between points A and B on the crack front and point A, point B here, A and B, you can see that K1, also you can see here that K1 values between points A and B are different. Why? It's 3D structure, okay? Then position of these points are different. Okay, it's not one single point. And then there's also influence from one node to another node, okay? And then as a result, we don't have, constant values along the crack front. So this is why crack can grow and move in different directions, not making, crack in the plane, but out of the plane. What is the kink angle? Kink angle is here. This is the formula used by Frank 3D. Kink angle is used to find the possible direction of the crack growth, okay? And it's based, of course, on the values of K1 and K2 in this case. And K equivalent. K equivalent is, there are many formulae for K equivalent. Different software, they use different approaches. But K equivalent is something like we want to find one single value which will represent both K1 and K2, okay? And kink angle formula, you can see here again, based on K1 and K2 values. So this is why we desperately need stress intensity factors in order to evaluate the possible crack paths. Okay. And then why I put this here on this slide, especially because today we're not talking about ANSYS application of crack growth simulation, because this is what I'm been using in the last 5 years, honestly. I moved to ANSYS in order to analyze crack because for some reason, I mean, the guys who developed extended finite element method and companies that accepted it and used that code, integrated that code in their software are not developing it anymore. I don't know why. Maybe.
Because I'm also using ANSYS Smart. So do you think it's better when compared to Abacus and all of the softwares available, it is better to go with ANSYS?
Look, for students and especially for PhD students, I highly recommend Abacus, okay? Because you can write your own codes, you can implement your own things, develop finite element new if you want, okay? Which is not possible in ANSYS. In ANSYS, you use the database of the existing elements and you're limited from that point of view. But in last few versions, they opened their code a little bit, okay? And you can write now your own code in Python. And also why ANSYS is so good, because you can go to a website, download your own version, student version for 1 year free, full version, okay? It has some limitations, okay? But you can work on it for 1 year and then, move to, I don't know, professional version or a version for research. For example, at my university, we have 1 license for professional use and 16 or 20 licenses, educational and research licenses. And it's easier to use. They all the time they're, developing new things. For example, in the last couple of versions, I can implement all those, NASGRO, Foreman. Yeah. Then also, what is good? I can analyze assemblies, which is very important for me because most of the aircraft structures are, assemblies. And I need to see what's the influence of one part to another part, then to simulate the contacts. So now it's possible to simulate bonding, frictionless contacts. The biggest assembly I analyzed using this was with more than 100 parts. And you have 100 parts in the assembly, and then you initiate crack at one of them, and you can analyze the complete structure. Of course, you can simplify that. And this is usually what I'm giving to my students. I tell them, okay, you have here 100 components. Okay, just eliminate all 98 and use only 2. Okay, I want to see how you're going to do that. Yeah, please. Yeah.
I'll check myself, but is the smart version of recent ANSYS,
yeah,
which allows you to write a code in Python,
yes,
does that also include
yes,
writing a user element or a user
no,
material?
No, not yet. But you can define your own material. Yeah. So no, I was, I think, clear. No. At the moment, no. But again, for all of you, I recommend Abacus until you finish your PhD studies. Okay. After that, move to ANSYS. Okay. For look, for commercial purposes, it's faster, reliable. You have very nice support. Okay. Let me give you another example. Abacus is owned by a company which is called Dassault. Okay. And the same company owns CATIA. You probably heard about CATIA. And when I import CATIA assembly into Abacus, Abacus splits that, explodes that. And then I need to define all components connections manually. When I do that in ANSYS, automatically I get connections and it's faster. You can come to solution. In industry, time is money. You can say to industry, hey, Boeing, hello, I'm going to develop my own finite element weight for 2-3 months. Say, come on, are you joking? I need a solution for this in 7 days. Mostly all the problems I'm going to show you now, they call me from the company and say, look, Aleksandar, we have a problem. Like Houston, we have a problem. Can you solve this in 7 days or 10 days? And then you must sit and try to solve. So this is why I recommend ANSYS for commercial, especially for commercial when you have to solve some industry problems. They don't care so much about science nowadays in the industry, okay? They care about, that's right. So Yeah, many. So, and also here I put some examples of the use of the ANSYS just to compare the results. Okay, you'll see that. Extended finite element method. Again, technology developed in, let's say, first decade of the 21st century. And when I first heard about that, it was completely new. And, you know, I didn't know what to do. First, I had to sit and read all these very complicated formulae, try to make my own code, which was not successful. Okay. And eventually, Abacus implemented that code. And then I did some of these simulations they're going to see today in Abacus. In XFEM, you don't need to map the mesh between geometry. I told you, in Frank 3D, when you create a new crack, it's new shape of geometry. So you need to remesh that again and again and again and again. In XFEM, you don't need to do that, okay? You need one mesh, and that mesh will be used through the whole simulation, okay? So a number of nodes is not changing during the analysis. So let's see, again, the same thing I used in the same problem I used in the Frank 2D and Nasgro, now Abacus. And you can see here, again, I made here denser mesh around the hole. And here I use quadrilateral, and here I used, I mean, no, not quadrilateral, these are 3D elements, So these are hexahedral elements, and these are tetrahedral elements, okay? In order to compare the results. Because one of the most important things, I believe you know that in finite element analysis, is the quality of the mesh. So what is the number of nodes, due to what shape of the element, what kind of element you're going to use, and so on. So it looks easy, but in fact, it takes a lot of time, please. Because here I grew only crack in that direction, you know, not in both, just in one direction. And also, look, I did this 12 years ago. No, 14 years ago, 2010. And at that time, you know, also, I mean, this kind of calculation took about, let's say, 10 hours. Okay, nowadays it's like half an hour. Okay, so I just wanted to save the time, and I didn't simulate crack on both sides, just on one side. And you can see how it looks like. So initially here you insert the crack. How? You simply make one surface, okay? That surface might have the shape of the penny, or a rectangle, or triangle, whatever, or half a circle. So here I use simple rectangle, okay? And you can see here, it goes through the elements, and you can position that wherever you want, between the elements or through the element, it should work, okay? And you can see this is crack opening here, then crack after 9 steps, so 1, 2, 3, 4, 5 steps of growth, which again can be done manually or automatically, okay? And then after 17 steps, you can see here on the crack front, you can see these different colors, which means, so here I use the stress to show you that stress in different elements is not the same, okay? Because it's influenced by the others, by surrounding elements. And you can see here, again, between point A and point B, I mean, left node and, I mean, right node of the crack front, we don't have the same values for K, so they are different, as we saw in example with Frank 3D. And again, comparison. Okay, now hexahedral elements and tetrahedral elements in XFEM compared with Nasgo and Frank 2D, you can see good agreement, okay, not perfect. I mean, as you can see, these tetrahedral elements, which are red, are much closer to Nasgo solution and Frank 2D solution compared to hexahedral elements, which is also interesting because, you know, one of the first lessons they gave me when I was a student that it's better to use hexahedral than tetrahedral, but it's not always the case, as you can see. And yeah, now we can see, sorry, let's go back. So it should work when I click on, no. To see, okay, maybe I can click on, I don't know why it's not, yeah, just to see how it goes through the structure. No, Okay, trust me, it grows. I mean, we tried, but for some reason now it's not. Oh, this is video. Okay, specimen. This CT specimen. Okay, again, this is solution from NASGRO. You can see, you can check, and you can take from this specimen from the database. You can pick your own material. Here, we have theoretical solution for K1, and it's like this: P times Y. Y is the function of the width and thickness of the specimen. And here we have also W is the thickness. You can see here what is C, what is W, what is B. And then this function Y this is formula for function Y obtained using analytical approach. Okay. And when you use theory, result is this. Okay, result is 297 megapascal millimeter square root of millimeter. So this is a little bit weird unit for this. And okay, using abacus, the same model, I got 292, which is difference is about 157% only, as you can see, compared to tetrahedral in tetrahedral mesh, as you can see. And in NASGRO, its difference is 5% using boundary, which means that XFEM is more accurate. And I use NASGRO as a reference, but in fact, it looks like XFEM is better. And you can see here mesh density, which I use here to get solution. This is ANSYS solution. Check 0.026% difference. So almost exact result. I was really surprised when I got this because again, I did this like 12 years ago in 2012, these simulations. And this is what I did like 2 years ago or couple, maybe 4, I'm not sure. And then I realized that solution in ANSYS is the most accurate, which means they improved the code dramatically. Plus, when I started using Abacus for this, ANSYS didn't have TOL. So you couldn't do that. You couldn't do any simulation of the crack growth in ANSYS, especially not in 3D. You could in 2D, but in 3D, no. And over time, they simply improved the code and made this much, much better. Again, this is video, but I cannot run it. This works. Nice. This is ANSYS. Yeah, 2020. So I did this like 4 years ago. Okay. You can see, and you can see here the change of stress intensity factors over time. And the same result from Abacus, but these images, I mean, these videos are not working. I don't know why. CCT specimen, again, 12 years ago in Abacus. And this is non-standard specimen invented by me, okay? So I just wanted to play with some yeah, please.
Talk about most accurate. Are you comparing it to the analytical?
Yes, analytical. Because check this, ANSYS 297, you can see it clearly here, 297. And analytical solution, 297, 187. So the most accurate answer. But, okay, what is the problem with ANSYS? You need to generate mesh with every new step. Okay, so they use that the traditional approach. So with the new crack geometry created, it has to remesh the domain. Okay, so it takes time. But over time, number of nodes becomes bigger and bigger, and your quitter is slower and slower. But what is good thing about ANSYS? They are, you send them a letter. Because as a customer, I can send and say, okay, so why you don't do this or do that? And they accept that. They accept that. So in last couple of versions, after crack moved through some area, and now that area is now not of the interest. So they remesh that area and reduce the number of nodes, which means that you can get even smaller number of nodes at the end of simulation compared to the beginning of simulation. I said, for example, method, the number of nodes is the same all the time. So it doesn't change, okay? But for NASGRO, and especially for assemblies. Okay, so why these examples? Because this is usually the first step. I mean, to validate your approach. and your models, you need something to compare with. Okay, so I can compare only with analytical solution or well-known solution from some other sources. Okay, but the goal here is not to simulate crack growth in a specimen. Okay, the goal is to simulate the crack growth in structure, real structure. But we need this to see is our approach good or not. Okay, and to analyze what is the best mesh, what is the best element to use. Yeah, also this no standard, and also this is very, famous example of 3-point bending. Okay, here using the standard element method, in this case I got very good agreement. It's like 97% the same as in theory. There is theoretical solution for this too. Okay, case studies. Yeah. Okay, I spent almost less than 1 hour. So what is here? I mean, usual procedure. We make a break after. Perfect. Okay, so we have enough time for, let's say, 1 or 2 case studies before the break and 2 case studies after the break. Good. Okay, now let's see implementation of all these things into reality. Because don't forget, science is very important. Science gives us many solutions, many first steps in further development. But science is useless if we don't use that in practice. Okay, so I mean, why science? Science just for science doesn't make sense. Let's not forget that many great inventions came from, let's say, NASA program Apollo, first moon landing, like Teflon, for example, or what is Teflon? It's material that our mothers or grandmothers are using for cooking the eggs or something like this. Now it's widely used, but at that time it was used as material for insulation. Okay, and many other examples. So I strongly believe that if we do not apply this in solving real life problems, then it's all useless. Okay, so let's see how this looks like in a real life examples. Case study number 1, damage wing fuselage attachment. Of course, you can see here again, all examples and studies are from development of aircraft structures. Many of these used in the development of some flight vehicles. You will see this very soon. It's okay now. My voice is back. Okay, good. Okay, first example, damaged wing fuselage attachment. What is this? Approximately 14 years ago, I was involved in the project of design of one light aircraft and finite element model of the fuselage you can see here. I cannot show you the whole model and the whole aircraft. It's not a secret, but I don't have rights. But I have rights to show you what I did, okay? That time, we used FEMAP, as you can see, software for finite element modeling. Why FEMAP? Why not some other software? Because we had a license for that. We didn't have a license for ANSYS. And NX Nastran. And you can see this is the fuselage. I mean, this is, as you can see, shell structure, thin wall structure. And here, these areas here and there is where we attach the wing to the fuselage. Okay. And that attachment, this is the finite element analysis of the wing. We identify the weakest and the most dangerous elements of the structure. And then this is, I must proudly say, what I designed, this whole here thing, okay? And you can see we have one part on the fuselage, is this one, and another part on the wing, and that's this right one. And we connect them here using this pin lug connection, believe it or not. This pin lug connection is the only thing we use to connect the wing to the fuselage, no other elements. So we simply, you can see, here, we have lugs on, we call this women part and male part, okay? And then here we just, using hammer, we put the pin inside, tick, 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 that's all. And this should hold the wing, okay? Now you understand why fatigue design of this here part is critical, because if you lose wing during the flight, there is no a rescue mission that can save your life, okay? So First thing was here to analyze using wings loads from the wing. So this is why I'm telling you we use ANSYS, because I can analyze complete assembly and get realistic results without any simplification. So we got here where is the area for the high stress. And again, I used my first love, okay, Frank 2D, to analyze here the growth of the crack in this slug. Again, I use this because I need something to compare with, okay? That time I could use only this. And then, because it was 2011, so I told you that Abacus started using XFEM code in 2010, I think. So this was one of the first, I'm not joking, first in the world, attempts to do some calculations, because I didn't have any manual, I didn't have any kind of instructions how to do that. You simply use a method which is called trial and error. Okay, so as you can see here, first I here use the crack corner crack here, which is a half of the circle, and again you can see I use two different elements, hexahedral and tetrahedral elements. So initial penny-shaped crack in hexahedral and in tetrahedral elements. And after 6 steps of propagation, you can see here, this here crack, direction of the crack growth varies, as you can see, which is in a line with what we see here, right? Okay, but this is, very simple model compared to this model here. And then this is what I got in these first simulations. And then using that previously described approach, you find K1, then you use Nazgo equation to integrate, blah, blah, blah. Okay, I got here a number of cycles which will grow the crack from 2 millimeters, which was initial crack, to let's say 8. Okay, we can see the difference. There is difference between tetrahedral and hexahedral, but definitely we should trust to tetrahedral elements. We saw that in the previous simulations, but okay, why I'm showing you this slide, be aware that mesh influences results. Not only number of nodes, but type of the element. And we can see that number of cycles here is very low, which is expected. Why? Because this element is not should be fail-safe element. So it's not allowed for any crack to appear on this element, because it's very, under very high stress. So it must be made of very strong steel, but the steel is very expensive. I know when we got the receipt for this element, when they made this for us, and then I was under the blame because I designed it. They said, yeah, it's very expensive. You could design something better, blah, 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 cheaper. I said, look, guys, this is what we have. If there is a crack there, we have a problem. So I designed it to never have a crack. Okay, I didn't show you here what is the number of cycles for crack initiation. It was more than a few million cycles, which means it is very, very. One also very important thing. Okay, here we are always talking about number of cycles. Does this mean anything to you? For example, you, girl or lady, you asked me one question before. Now I'm asking you one question. So what do you think? Is 400 cycles okay? But what is 450 cycles? One example, a couple of years ago, I was talking to my friend. He is an expert for weapon systems, so nothing to do with aircraft. And he's designing cannonballs. Okay? And we were talking about life of the components and so on, and asking what is the life of the cannonball barrel? You know what is the barrel? That big pipe, and then you're firing grenades through that. He said 7 minutes. I said, what? What 7 minutes? Are you joking? What is 7 minutes? So I go to the battlefield, and after 7 minutes, I'm dead. He said, no. Time to fire one grenade is 0.14 seconds. So 14 hundredths of the second. So within 60 seconds, which is 1 minute, you can fire 428 grenades. Okay? 7 minutes means 7 times 400, you get 3,000. After 3,000 grenades, you need to replace that part because it's damaged. Understand? But it's 7 minutes. If you measure time, it's 7 minutes. But to fight 3,000 grenades, maybe a couple of months, or I don't know, days, depends, okay? So when you say 450 cycles, this must be 450 weeks or 450 years. So my point is that you have to define the cycle. What is cycle? In this case, cycle is you have a maximum load and it pushes your wing up. During the flight, wings are always up, okay? So that's one cycle. So here, 450 cycles of the maximum load means like a couple of minutes. I mean, many lives, have been lost in the past because of this. I can tell you several examples, but better not, okay? So crack here is not allowed. And I prove this in my here design that if crack appears here due to very high stress, crack will grow very fast. And here you have, literally have a couple of minutes to survive in this case. So another example here is the use of true crack, which as you can see, grow through the complete structure, not only it starts from this, not from one corner. And then again, comparison with the results from ANSYS. Again, I did this like 14 or 12 years ago. I really can't remember, but I did this like a couple of years ago. And then when compare these results, okay, I said here, finite element, extended finite element. So we can see again, good correlation between them. But in fact, you can see that when using ANSYS, you have less these variations, as you can see here for extended finite element method. If you ask me which of these two is better, ANSYS. Okay, again, I explain why, because ANSYS creates a new mesh with every step. It does automatically, which is a good thing. And here, definitely you have to play with the mesh. In ANSYS, you can literally start with a very bad mesh, but you improve the mesh only around the crack front, okay? And then it goes very, very nice. Here, you have to improve the mesh of the complete model. That's the problem. Understand?
This comparison, you're not referring to XFEM from Abacus.
Yes, Abacus, from Abacus. Yes, from Abacus. Comparison of these results here. This is Abacus. And yeah, we can see more or less. What is one of disadvantages of ANSYS? You can use only tetrahedral mesh here. But the reason is simple. I proved that tetrahedral is better in XFEM too. So you cannot create here hexahedral, only tetrahedral mesh. So they learned probably from some examples from maybe they read my papers. I don't know. I'll ask them next time. Okay. And also you can see here, result is much better when we have this true crack. Difference is very small now. Check this. Difference is very small when you talk about true crack, okay? Between Abacus and ANSYS, and this previous is for edge crack or corner crack. So maybe also some interesting thing to study. Okay, again, probably we cannot see here because all these from Abacus movies are not working. I don't know why, but okay, again, you can trust me. Yeah, another example, crack growth in the wing spar. Okay, so here in previous example, I didn't have experimental validation, okay? But in this example, I have. This was part of my work on my PhD work, my PhD thesis 15, 20 years ago. And we analyzed, as you can see here, fatigue life of the wing spar. What is the wing spar? Wing spar is maybe the most important part of the wing, okay? It's the main beam and carries most of the load during the flight. And position of the wing spar, it's here, you can see. And there, this part of the wing spar belongs to the fuselage, and there is the same part here on the wing, okay? So I analyzed this part here, you can see here, and it looks like this. So we call this differential spar. Why? Because it consists of several parts, so it's not integral. So we have here, as you can see, spare caps. So spare caps are these L shapes, L beams. Spar web, which is simply plate with some thickness. And here you can see fastener holes, supporters, strengthened washers, and so on. And as you can see, again, this is the wing root assembly of the light aircraft, and this is that crucial part made of aluminum 2024 T3. So this is our experimental setup that we used in our study. Okay, I'm not going to describe in detail what we did here, but basically we applied, so SPAR is here. I hope that you can see it here. So basically we applied here using this adjustable drawbar, we applied displacement at 3 ends of the SPAR, okay? And using 3 Hertz load, we applied, this kind of dynamic load. We measured here using these devices. We applied, this is called a narrow band random loading, and it's one of the loadings used in analysis, in fatigue analysis of aircraft components. And this is what we came up with. Okay, first, I did this later, honestly, because again, at that time we didn't have ANSYS. But I wanted to prove that this is really the area where the crack will appear, but it's logical. Come on, this is kind of clamp here, and then the stress is the highest in a root, which is here fixed, okay? So obviously this is the area where you should expect the crack to occur. And then using a fatigue module of the ANSYS, I evaluated that crack here will appear, as you can see, after approximately 8,000 cycles. In reality, we got it after 7,000 cycles, so faster than my, but again, I did this after experiment, not before experiment. But it fits well, as you can see, to results of experiment. And then this is what we got. In fact, we got 2 cracks. One on the left cap and one on the right cap. So the first crack started here somewhere in this area because we couldn't see. Later we analyzed that. Of course, we didn't analyze only one SPAR, we made 10. So in experiment we used 10 10 same SPARs, okay? Why only 10? Maybe someone might say, why not 200? Look, in aircraft design, see one big series in aircraft production is like 1,000 aircraft, you understand? So in an automotive industry, for example, Toyota makes 7 million cars every year, but Boeing makes only 300 to 400 airplanes every year. So we cannot afford to destroy like 20 or 30 SPARs because it's very expensive. Aluminum 224 T3 is very expensive. So we made 10 samples or 10 specimens, and then we did 10 experiments. But I'm showing you the most interesting results. So first crack on this SPAR cap, second occur here on a fastener hole, and then cracks, because I told you this is in fact L beam. So crack appeared here on the horizontal wall and then move along the vertical wall. So you can see here the images of the crack pads on the vertical walls. Again, you can see here the damaged SPAR after experiment. So completely, as you can see here, destroyed this cap, so completely useless. So again, Frank 2D, I use them first. How? I made it's 2D software, but I managed to make it like it looks like 3D. Why? I made 3 layers because there is a Frank 2D software and Frank 2DL. So that L means layers. So that's improved version. So I made 3 layers. One layer for for vertical cap, one layer for wall, and another for second vertical. And then look what I got as a result of simulation. And I use here automatic mesh creation. Automatic, I just wanted to see what's the result of the simulation. So check this. Crack growth here compared to this. And here crack growth here compared to this. You can see almost identical. And you can see here in this dashed line, so that's the a crack from the other side, because this was done at the same time. Okay. And I was really thrilled when I got this, because when you compare this to, what you get in experiment, it looks really amazing. But again, it was only 2D simulation. I couldn't do this so I couldn't simulate transition from horizontal to vertical wall until I got Abacus XFEM. Okay, again, using previously described approach, I got for the first crack that life is about 13,000 cycles, for second crack 40,000 cycles. By the way, we stopped the experiment after 56,000 cycles. We used very high load because we didn't want to wait for days to get the crack. Okay, so we just wanted to, okay, honestly, we did not expect to be finished in less than 1 hour, okay? We estimate like 2 to 3 hours, but we damaged, completely destroyed the spar after, I told you, no, not 1 hour. So it was 3 hertz. So it was 3 per second. So we can calculate easily what is 58,000 cycles. XFEM calculation in Abacus. Here I could, design and, simulate complete spar with the right boundary conditions here. I apply displacement on this side, pre-end. This is how we insert cracks in XFEM. You simply make one surface, arbitrary shape. Here I use circular shape. Okay, I didn't have the evidence that the crack started really here, but definitely started somewhere in this area. Probably it started here because we couldn't see. We couldn't see, and honestly, we didn't expect it to be finished very, very fast in this case. And we started crack here, and you can see again in this area, I made a very dense mesh. And then you can see here, first crack growth along this horizontal wall of the spar cap, and you can see here the image from experiment. So you can compare this with this. Then transition from a horizontal wall to a vertical wall here. You can see it's going through to this area. And finally, complete failure of the L shape after 45 steps of propagation. In fact, total length of this is 45 millimeters. And so this means that with every step, crack grew 1 millimeter. And compare this to original crack PET, we notice this. Look, in experiment, crack move like this, but then along this direction, and finally this. You can see it here. Moves like this, and then goes to this here hole. In our experiment, we didn't get that. I'm sorry, in our simulation. In simulation, I got this. And I was wondering why. Why? Okay, maybe I made some mistake, maybe. But we realized, because we ordered these from one company, we ordered these spars from one company, so they made these spars for us. So I called them and asked them, okay, did you use any method for stress relief after you, form this? Because all these parts, we use rubber pad forming to get these parts. Maybe you know what's that. Maybe you don't know, never mind. In aircraft design, 95% of the parts are made using rubbing pad approach. So you have a tool, you put a blank on the tool, and then you have a rubber pad, and you apply pressure, and then part is formed around the tool. So this is how we produce that. So, and it's very important after that to use stress relief methods, okay, because you have some residual stresses after that. So my conclusion was that maybe there is some residual stress here. So we order and pay new spar in which all parts, went through heat treatment, and what we got, new PET, looks like this. In another experiment with the same part, but where, as you can see here, we view the crack after stabilization, residual stress removal. So they remove residual stresses. So definitely this PET was caused by, that was my conclusion, was caused by residual stresses after rubber pad forming. And this is also a good thing because this shows us that sometimes numerical approach can help us to understand what is wrong with our structure, especially if you are sure what are you doing, and if your calculations are, I mean, if you didn't make any calculation, I mean, error in a process of making your model. And unfortunately, again, we cannot see this image, but it shows how crack grows. And this is calculated stress intensity factors. In this case, I use K equivalent. Why? Because when you have, when crack grows in two directions, first it goes horizontally and vertically, then K1 and K2 will not be the same. So this is why I have to use here K equivalent. And again, using, you know, NASBO equation. No, in this case, I use Paris equation because at that time I still couldn't apply that and got coefficients. I mean, I use coefficients which I took from the literature. I must be honest here. We didn't do our own experiment, but we got number of cycles which is very close to the experiment. Look, 50,000 here compared to 58,000 obtained in experiment, which is pretty good. I mean, agreement between this, especially because I used coefficients for Paris, which are not my own coefficients. I didn't get them through my own experiment. I took them from the internet. And, you know, if you use some other experiments, you get different results. I mean, some other coefficients, sorry, which is also my point here. If you want to apply any of these laws for a prediction of, to predict the number of cycles, you have two options from my point of view: to use NASBO, which are really reliable because they did hundreds of experiments, okay? Or to carry out your own experiment, take a sample from your material, do experiment with specimen, and find coefficients. Okay, what time is it? Okay, we still have some time before the break. Any questions about this? Okay. Yeah, few slides about what is the next step after this. Okay, so in my simulations, I used you know, that load that you saw on one of previous slides, load from experiment. But the main idea here is to estimate the number of cycles in reality, in real flight. In aircraft design, we usually use these are standard spectra. Okay, this is called mini twist spectrum. This TW is for transport aircraft, okay, or transport vehicle, blah, blah, blah. And this is spectrum for fighters, for, I mean, these military aircraft. And you can see what's the difference here. I mean, it's very interesting, right? Because this was recorded during the flight. So for, I mean, fighters, I mean, the most dangerous and the fastest aircraft, okay, we can see we have a very large, I mean, here range between the mean and maximum values during the flight with very high peaks, as you can see here. But for transport aircraft, we have only a few and much smaller peaks, okay? And also we can see here that, okay, maybe you cannot see these numbers, but for example, it reaches maximum only once during the over time, and here many times it reaches these maximum values. Also, here you cannot see, but it says 50,000 cycles. My question for a lady before was, what is 50,000 cycles? In this case, we're talking about 13 hours. 13 hours of flight, that's 50,000 cycles. It's 1 cycle per second, okay? So this is, I mean, what they recorded over 13 hours. And this is here 18,000 cycles, which is about 2 hours. It is about 2 hours, or not 18, maybe less, but I remember it's 2 hours, because this is average of flight time per day. Military aircraft, I mean, especially fighters, they don't fly more than 1 or 2 hours per day. Why? Because the consumption of fuel is very high. If they are not in combat, then there is no need. So it's mostly for training of the pilots, so 1 to 2 hours. But commercial transport aircraft, okay, 20, 30, 14 hours. Also, maybe some interesting facts from the aviation. So if you're a company, I mean, if you're a commercial airliner, okay, and then you want to make a profit, and you, let's say, you don't have your own aircraft, you rent them. Okay, or you're using leasing, you know what is leasing, right? So what do you think? What is the average number of hours that your aircraft must be in the air during the day, during one day, in order to break even? You know what is break even? And your profit is zero. Okay. So what do you think? What is the number of flight hours per day for commercial aircraft to break even? 14 hours. So if the aircraft is not in the air for 14 hours every day, it's not profitable. It's not profitable. For example, yesterday I came here from Belgrade by aircraft, of course, and flight took about 1 hour and 15 minutes. So this is a one-way trip, right? Round trip is then approximately, let's say, 3 hours, okay? So they have 3 flights per day, Belgrade, Zagreb, in the morning, in the noon, and in the evening. So in total, it's nine hours. So I say this is not profitable. Not profitable. But if you're flying from Belgrade or Zagreb to New York, for example, and back, it is profitable because it takes something like one way is 8 to 9 hours approximately, and back it's 16. So you earn something during that trip. Of course, on assumption that you sold 85% of the seats. If you're empty, you earn nothing, even if you're in the 24 hours in the air. Okay, so why I use this example to explain why here 13 hours and why here 2 hours only, because this is average use of the aircraft during the day. And using this spectrum, okay, I got for second crack approximately 2 million cycles, and for first crack about 1 million cycles. So now this means, something like 200 hours, as far as I remember, 200 flight hours, which means that when you see that crack during some expansion or during some repair of the aircraft, okay, and you see there is a crack with a length of 2 or 3 millimeters. So then you should say, okay, if you use my calculations, you will say, okay, in next 200 hours, we must do something, because in 200 hours, it will fail. Okay, 200 hours is a long period. It's something like 20 days, let's say, or 15 days. So when they see crack on the spot, they must do something in the next couple of days, because you don't want, to put lives of your passengers in danger, because you do nothing and you wait. Okay, I still have time. Okay, because Aleksandar from Belgrade told me that we have 200 hours. So we never do that. By the way, in practice, when we calculate that, for example, this component will fail after 100,000 cycles. We divide that by three, and say to airliners, okay, after 30,000 cycles, you must do something. So understand, this is safety factor. Safety factor is 3. So we'll never say, okay, you have 100,000, okay, replace after 90,000. Never, replace after 30,000. There is always pressure from the airliners. Oh, can we postpone that for a week or 2 weeks? Because if they land the aircraft, they lose the money. You understand that? Because to fix something like this, it takes like 2 weeks. You have to disassemble the wing, to take this part, to break all these connections, to put new part, then make connections. So it takes usually about 2 weeks. 2 weeks on the ground, huge loss for airlines. So it's a battle always between designers and engineers, where CEOs of the companies, usually, because they just look at the numbers. They don't care about, unfortunately, okay, better not to say. And finally, because we saw that usually these cracks, they appear on these holes for fasteners or rivets, okay? So I did calculations in order to analyze what is the possible crack path if the crack appears not on a spot that we saw in the experiment, but on these 3 holes. You can see here, almost 600,000, here 6.2 million cycles, here 69 million cycles I mean, if the crack appears here on this hole. And you can see here comparison. And we got, just let's not forget, we got around 60,000 cycles in experiment. So definitely here the most dangerous spot is here, but B is here fastness. If the crack appears here, it's not that dangerous because the stress in these areas is not so, it's not so high. Okay, 10:25. Okay, 5 minutes to finish this. Then I'll take my coffee. Another approach to this problem, how we can improve the fatigue life by redesign. Again, in aircraft design, it's very important to keep mass low, okay? So if I want to replace that original spar with another design, I must provide the same weight. In other words, all these here alternative designs, they have the same cross-sectional area. If the cross-sectional area is the same, length is the same, so mass will be the same material. But what is not the same here, moment area of inertia, okay? And so here we played with different, okay, this is again I-beam, like original I-beam. But what was the difference? The original spar was differential, made of 5 different parts, four caps and 1 wall. Okay, here this is integral design obtained by laser beam welding. So what's the difference? Here we don't have, mass will be even less because we don't have rivets here. We don't need rivets because we have integral structure. And all 3 integral, and here this is I-beam, we're intermediate flange here. So we here play with 3 different designs. I mean, these, you can see C1, A1, B1, all these here. I mean, almost 10, I think, different dimensions in order to find the best solution to improve fatigue life without changing the mass, not changing, reducing the mass of the wing. And again, we use the same approach in a design. You can see here, this is U-shape. This is this with intermediate flange. This is I-beam, but integral I-beam without rivets and everything. You see no rivets hole. And again, here we initiated, when I say we, this was the part of the PhD work of my student, okay? So here we initiated the cracks as usual, and then got, as you can see here, different shapes of the cracks here growing through structure. Since we got 2 cracks in original differential spar, here we initiated 2 cracks, one on this side and one on that side. What is interesting here is that they didn't meet here. I mean, they grew. Why? Because this one stopped. Because pressure on the beam was such that stress around here, around this crack tip was compressional stress. It was compression, not tension, okay? And this crack stopped, which is also interesting. So this design can even stop at the crack on one side of the, if two cracks appear simultaneously. I mean, what is my point? Using numeric methods, you can play with a lot of things and then improve your design, okay? And yeah, now comparison of simulations results for all 5 cases. Look, the worst case, it was integral I-beam. It was around 200,000 cycles. So 3 times longer life than original differential spar. But I-beam with intermediate flange, 1.4 million cycles. 1.4 million cycles. So it's something like, I don't know, 25 times longer fatigue life with crack than initially. And then I said to manufacturer, use this. They say, no, it's a long way to certification, which is true. In order to change something on the aircraft, the smallest thing, you need to wait a couple of years because it takes time. You have to prove your design. They have to test that there's some international committee. Then you have to go there to defend your design, to prove with experiment. It's usually very expensive. Okay, money on one side, but the time on the other side, the time is crucial here. So we unfortunately never, made it to the market with this improved design, but at least we proved that this improved design is, can increase fatigue life with the crack 25 times. This next example is very interesting. And this is one of examples in which I admit I failed to predict what happened until February this year. I was working on this example in the last 5 or 6 years and couldn't get results which are in the line or in the good agreement with experimental. And it bothered me much, and I was thinking about this all this time. And this February, this year, I found the solution. Unfortunately, that solution was not in Abacus or XFEM. I did it in ANSYS. I have that on my laptop because I expected that my laptop will be connected to the screen so I can show you this. But okay, maybe after we finish this, if you're interested, I can show you that on my laptop. Okay. Okay, what I'm talking about. Fatigue life assessment of damaged integral skin stringer panel. Okay, this was not my project. This was a project of Airbus company. And you can see this is the image of Airbus 380, one of the biggest commercial aircraft in the world. And during their development in the beginning of the 21st century, development of the aircraft, they worked on so-called skin stringer panels. These skin stringer panels are used here on the tail of the Airbus 380, then on the fuselage here in this area, and also some of them are used in the wing of the aircraft, and they look like this. Okay, so it's this thing here. There is a plate, okay, with some thickness. In this case, I think thickness was 2.6 millimeters. And these longitudinal elements, you can see them, are called stringers in aircraft design. So they carry load along their horizontal axis, okay? And I told you before and explained that on the example of the spar. That spar that you saw in previous case study was differential spar made of several elements connected together by rivets. And you can see here, this is also stringer, this is skin, and there are rivets here also there to connect them together to close the structure, to make something that we call a wing box, okay? But modern design is this integral structure in which we don't use stringers, but instead of that, we use laser beam welding in order to connect stringer to the skin. And you can see here the difference. Here we have a stringer. In this case, it's Z shape. There is a skin here and rivet here connects them together. In this case, there is stringer, skin, and welded. Laser beam welding is used to connect them. So what is the advantage of this design? You can disassemble this if there is some failure. You can simply remove rivets and remove the stringer and replace with another one, okay? In a case of integral structure, you cannot do that. If something here fails, you must replace everything, okay? There is no here fixing. And, but advantage is lower mass, okay? And during design of the Airbus, one institute in Germany, in Hamburg, it's called GKSS Research Center. They work together with Airbus on fatigue analysis of these skin stringer panels. And you can see here the dimensions, you can see shape and dimensions of the stringer. So this is the device they used for experimental investigation of the crack growth in these panels. And this guy you can see here, he is responsible for this case study because he used to work for this institute. Then he came back to Belgrade after he retired, and he brought some of these images and results from that institute, okay? And then I started to play with this design. This is what he also gave me. Initially, they tested base metal panels. So it's just a panel, I mean, with a thickness and a crack in the middle of the panel. But basically, this is CCT specimen. Okay. Okay, the dimensions are bigger. It's not small. It's like, you know, you can see on previous slide, it's like 760 millimeters and 1,200 millimeters. It's, I mean, rectangular shape and crack in the middle. And first they tested this base metal panel without stringers, so just the skin. And they used two materials, aluminum 61566 and 61564, okay? And they got this, look, number of cycles, crack length, okay, different for different materials. And here, they published this. They published this. Here, Paris law, coefficient C and M, okay? And I took this for granted. Okay, I took these coefficients. Come on, Germans, they did that. Is there any German here, guy or girl? Okay, see ya. And they published this, and I took these coefficients like, okay, they got these coefficients. It must be that, okay? And did my calculations. First, on base metal panel without any stringer. And you can see here I got the difference around 10%. So in experiment, you can see they reached the length of 273 millimeters after, let's say, 189,000 cycles. But in my calculations, I got something like 170,000 cycles. So you might say, okay, not a big difference. It's around 10%. My estimation is conservative, which means I'm on the safe side. So it's okay. And I didn't care a lot about this difference. Okay. Again, for Paris equation, I use coefficients that you saw on previous slide. And then I played with panel with 4 stringers. And of course, they initiated crack here in the middle in experiment, okay? Then they grew a crack and they, damaged all 4 stringers in experiment. So crack grew from initial, it was 14 millimeters was initial crack, and then it spread along this horizontal axis, then came to first 2 stringers, broke them, then came to another 2 stringers, broke them, and finally complete failure of the plate with stringers. And fortunately, this guy gave me Excel file from the machine with, you know, all these parameters recorded by machine they used in experiment. And then first I made this model. This is the model of course, in Abacus, where I used the size of the mesh 1 millimeter, okay, which is very, very dense mesh. And look, I managed to here break one of the stringers completely, and the second stringer here, let's say partially, which is good, not bad at all. And I got here around 250,000 cycles until 350 millimeters. I mean, when crack length was 350 millimeters. The problem was, you will see later, this was a difference of more than 40% compared to experiment. Then then I went to Paris to some conference where all the experts from the Europe for numerical simulation came, from Germany, Italy, France, UK, America, lots of people. And I showed them this because this was in 2018, 19. I mean, I remember before Corona, okay, merged. And they told me use less denser mesh. So this was their advice. So this is why here I used now, look, a mesh is 2 millimeters, and I got closer to 300,000. So the only change is I used the bigger size of the mesh. Then I used 4 millimeter size, even better results. So now almost 300,000. But unfortunately, in experiment, they got 420,000 cycles. So when we compare, and again, I used coefficients M and C for Paris, provided by Germans. Yeah. It works. Yes, we can see how this crack is growing and then destroying the first stringer and then partially the second stringer. But in my simulations, I managed to break all four after 100 attempts, because it's about, mesh density, it's about boundary conditions, it's about defining the step of the growth. There are many parameters that you can control and define, okay? But this was not satisfying because look, when I used 1 millimeter difference between experimental and numerical approach was 39%. When mesh was 1 millimeter, and when mesh is 4 millimeter, then it's 31%. As you can see, it's less than this, but still too much when you compare XFEM and experimental. And then I tried many other things, like adding here, weld toe. As you can see, weld line is here now presented, which was not presented in a previous. Then I changed a little bit boundary conditions just to see is there, something wrong with boundary conditions. Also, I did the same simulation in ANSYS, okay, but results always very different from experimental work. And then I just quit, and I say, okay, I don't know what is the problem, what is wrong with my calculations. I don't know, because I really trust experiment, And after a couple of years, this winter, I was, not busy at that moment. I said, okay, let me try something else. And then, I'm talking about you have to be, focused, and you really, sometimes you must leave things, okay, and do something else and clear your head and then try some other approach later. That's my experience. But this time, I did something else. I took all these numbers from experiment, okay, and studied them very, very focused. And I found a mistake. Then I calculated my own Paris coefficients from their experimental data and got less than 1% difference. Less than 1% difference. I wanted to show you this. I have this on my laptop, okay? But my laptop is not connected to this. So after I finish this, okay, if you want to see that, you can come to me. I'll show you and explain what I did and how I got results. What is my point? I could put that on this slide, but this is about XFEM, not about finite element method, okay? So, but again, if you want to see, I'll show you. What was wrong, briefly, what was wrong in their calculations? They didn't calculate well range of K, stress intensity factor. Because, they have all data from experiment. And basically, in experiment, when you deal with the dynamic load, you are trying to keep the maximum and minimum load fixed, like, for example, 180,000 newtons is the maximum value, and if you want to keep a ratio of 10%, then it will be 18,000 is the minimum value. But when you check results, recorded values from machine, you see that force is varying. Sometimes it's 18,000, sometimes it's 16, sometimes it's, because, over time, resistance of material decreases, okay? And, machine can adjust to that, but not 100% correctly, okay? So these guys, they use the maximum and minimum value just like it's fixed, not changeable over time. And when you do that, I checked their results. The Paris coefficients they got, they were calculated correctly, but the input value was not good. So I then, because I cannot, repeat this experiment, okay? I did numerical experiment, okay? I made a model and then I changed the values of the force as it was in experiment, okay? From this length of the crack to this length of the crack, okay? I changed the values of input force and calculated different delta K from them. Then when I use my results and calculate my own, coefficient C and M, I got almost perfect fit. almost perfect fit. By the way, I will publish these results very soon. I mean, so you'll also be able very soon to see that, because it's very interesting. I mean, okay, everything in that experiment was correct, okay, but their calculations too simplified, let's say, too simplified. But again, they did this in 2003, so 20 years ago. They didn't have tools that we have nowadays, you understand? So they used some of these methods used in the 80s and 90s last century, when you use some approximations, use some approximative formulae, okay? So my point is, experiment was correct, everything was fine, but values of C and M in Paris formula, not correct, not well estimated. But good news is that using these coefficients, I got, I mean, results which are conservative, which is on the safe side. So no damage will be done on any Airbus aircraft, so don't worry about that. I mean, from the point of view of fatigue design. Yeah, so these are images from ANSYS simulations. And also, they used here so-called clips, because they wanted to check, can we stop somehow or slow down these cracks using additional here elements? So these elements are called clips, okay? And then you can see crack is now growing along these clips, okay? And also I checked that and used simulations, and I got 5% longer fatigue life with used clips. So which is also in a line with what they've got in their experiment. Again, I did this in a finite element method in ANSYS. So this is why I did not put here these images. And finally, something which is not the part of aircraft design, but somehow in aerospace design, we use pressure vessels, okay? Because this was work of one of my colleagues, and then she came to me and asked me, can I help her with some numerical simulations, because she did experimental investigation. So it's about crack growth in the damaged pressure vessels. So this is pressure vessel used in experiment and in this simulation. I'm proud of this because of this simulation, because I did this again like 10 years ago, and the idea was to compare results with experiment, and then to see, can we predict crack growth in this kind of structure, which is not typical aircraft structure. So you can see the manus of the vessel of this vessel. Vessel was designed in CATIA, and I did that design. And this was experimental setup, pressure vessel with all these valves and these gauges. And here we use stereo cameras to record what's going on using so-called 3D digital image correlation methods. Maybe you're aware of this camera. So we use very fast cameras to record what's going on. And as you can see here, these two nozzles are close here together, and then this correlation method revealed that here this is the position of the maximum strain, which was about 0.20%, and this was the reference I used in my calculations to check, boundary conditions, pressure applied, and the quality of model. So I modeled here only 1/2 of the vessel, of course. And as you can see here, I did this in Abacus. I got here, it's not visible, but maximum is around 0.2%, which was almost the same as in experiment, and also position was the same. As you can see, this root of this nozzle. And then okay, we didn't do this. Okay, this happened in one firm in Serbia, something like 6 months before these experiments. So this was idea, to try to simulate this. Okay, this breakage here and the leaking of the gas from these pressure vessels. You can see here that crack grew in 2 directions along here nozzle, and here on the shell of the pressure vessel. So idea was, okay, let's see, can we do this? Can we get similar shape in this case? And then the goal was to redesign the vessel and to prevent accidents like this. And you can see here how I did this. You can see this is one of these nozzles. I initiated crack here. It was penny shaped. And this is so-called crack opening, and then crack growth. And here you can see the shape of the pressure vessel after 75 steps of propagation. Again, if we go back, you can see here it's almost the same shape of the crack and the same direction of growth. It grows in two perpendicular directions. So what is my point here? I mean, when you get something almost exactly the same as in reality, then you can be very satisfied, and then you have a proof that your design was correct. Yes, please.
Question regarding the sensitivity of the model. If you decided to install or use another shape of crack at the initiation part, does it have a big differences, and how do you choose this geometry of initial?
Yeah, good question. So look, basically, if you talk about pressure vessel, so these cracks, they grow very fast. It's like almost like explosion. And we got this, I mean, when I calculate the number of cycles, there's something like 0.1 cycles. So it means immediately, grows immediately. So in cases like this, initial shape is not so important. But usually we use penny shape. Why? Because, and also here I use penny shape. Because in reality, you saw that on that component of jackhammer, they are usually penny shaped and moving in that shape, okay? And even if initially, if it starts like, you know, use rectangular shape or some other, I mean, mostly I use rectangular shape for true cracks, like in that lug, and penny shape. And most software, they use the same, okay? In fact, you can define any shape you like. But in reality, what we know from experience, it's in 95% it's penny shape. When it starts to grow, it goes in all directions. Yes.
It's mostly because of the plane stress condition.
Yes. Yes. Look, let's not forget all examples here I showed you are thin wall structures. So that's your point. That's your point. But also here, I mean, we stopped the calculation after 200 steps. I remember it took something like 2 days. 2 days to get, because here I made very large number of nodes in this area. And then, of course, nodes are here not changing during crack growth, but very large number of nodes, so very large number of calculations. The last slide after this one. Okay, the last slide after this one is to show you how the output from the abacus looks like. I'd like to explain how, how you should handle it. And it's also not an easy job. For example, you just get numbers like this: 0, -277, -18, -118, 2478, 249179. So this is the output. And first you need to read that output, and later to process the data to get some values. For example, first number here is curvilinear abscissa along the crack front. Okay, so because crack front is some curve, okay, and then they use here some curvilinear abscissa along the crack front. But good news is you can also hear the next three numbers are X, Y, and Z coordinates of the node in a general, coordinate system, okay? And you can see -277 millimeters, -18, -118. Then next number is equivalency, stress intensity factor. Next three numbers are mode 1, mode 2, and mode 3. stress intensity factor, okay? I showed you before how this equivalent is calculated, but they use equivalent. Why? In 3D models, when crack grows in space, not in a plane, they use, and it's recommendable to use equivalent SIF. I showed you formula used for this calculation. So you have mode 1, mode 2. You can see that mode 1 is dominant. You can also see, and also mode 2 is negative, which means it will not grow. I mean, crack will not open in that mode. Negative SIFs means that crack is not growing. Also, there is here a moderate SIF3 mode. And we can see here that equivalent SIF is combination of these 3 values, and it's in this case 2478, which is very high. This is very high value because this is millimeter square root of, or megapascal square root of millimeter. So this is very, very high value. So this is why in this case I told you that I didn't here put a number of cycles because I got in calculation it's less than 1 cycle, so immediately. So this is kind of static crack growth, okay, when you have a very fast growth. Then next node with coordinates, next node, and then if you have something like 15 or 16 or 20 nodes on a crack front, you need to analyze each node, okay? And you can see here, and especially if you have, in previous example, we did 200 crack, I mean increments, 200 crack growths, let's say. I have put only for first 80. And you can see that number of nodes on the crack front is more or less constant. It's only 12 nodes because it's a very, very, you know, thin structure. And then along the front, you can see here maximum value along the front because for each node you have some values. You can see it's 2,400 and minimum is 1,784. But this is initial crack. And remember that crack was initiated in that area between the nozzle and the shell, okay? And then it starts to grow in 2 directions. But later, you know, after, as you can see, 20 steps or 40, 60, then you can see the difference is very small between the nodes. Why? Because it's growing on a structure with a constant thickness, okay? And here, especially because here pressure is from the outside, so more or less all values on the crack front are the same. Look, 3794, 3730, it's not a big difference between the minimum and the maximum value. So in my calculations of the life, I mean number of cycles, I usually use the mean value. I tried with the maximum value, I tried with the minimum value, I tried with the mean value, but usually mean value gives the closest values to what I got in Frank 2D or Frank 3D or ANSYS, okay? But again, in ANSYS, for example, when a crack front is formed, you have option to choose. Do you want to see SIFs for 0, 10%, 50% of the crack length, 100% of the crack length? So you can choose, and then you see it's different number of cycles, different number of. So sometimes it's better to use maximum value if you want to find the worst scenario and the worst case. But when the difference between minimum and maximum value is not too big, then it doesn't make a big difference if you use mean, max, or a mean value. But what is my point? You need to process the data after that. You have a lot of job to do, especially if you want to use different laws. Abacus and ANSYS, they use Paris law, original Paris law. But difference between values when you use Paris law and NASGRO law, for example, could be very, very different. Another thing to remember, crack closure. You know, what is that? I mean, a kind of closure I showed you in that, I mean, with the intermediate flange, that example with spar. And one crack stopped. Why stop? Because there is a pressure around the front. I mean, crack front and crack, I mean, all SIF values are negative, so crack will not grow. So in ANSYS, you can also implement, I mean, crack closure. And but you must write Python code. It's not supported automatically. You cannot just simple click on some icon, something like that. Also, all other laws like NASGRO, Walker, Foreman, you need to write a code. So it's not, only Paris is automatically supported, which means that you need to study ANSYS code. You need to, all the same thing for Abacus. The same thing for Abacus. So to finish with this, again, for us, I mean, engineers and scientists and professors, it's very important not to use science just for the purpose of science. It's important to know how to implement this in a real life problem solving. Okay. Here also I have several presentations which I wanted to show you just in brief. Another things that I did, another problems that I solved. One of the problem which I used the XFEM to solve that, and maybe the hardest case, but I didn't want to show it here because I showed it last year in Dubrovnik. Maybe some of you attended that meeting in Dubrovnik. I was online presenting this. It was simultaneous growth of 8 cracks in a honeycomb structure of an airplane. Okay, and what was the most amazing thing, and maybe I mean this is the most interesting thing. So when they find these cracks, so what do you think? How they manage that? For example, you are a worker in a workshop. There is a aircraft for maintenance there, and then you notice very long crack on the, let's say, wing or on a fuselage, and you have something like 5 or 10 minutes to do something. So what would you do? What would you do? How to stop this crack? Because sometimes they are growing very fast, and maybe next flight will be critical flight for. But that airplane must go. So what would you do? Very simple trick. You take a drill machine and drill a hole. Yes, drill a hole at the top of the crack. Yes. So it will stop a crack, not for a long time, but enough time to go to, I mean, to apply some patches later, let's say after next flight and so on. So this is what they do. They see that, and another thing you can do is to weld the crack. So in that another presentation which I have here, but unfortunately it's on my laptop, I had example of that. So they find very long cracks and they weld them. You take welding machine and weld the crack. After a couple of, I mean, months later, the crack is on the same spot near the weld.
It's misguiding the crack front.
Yes.
Like
Yes.
we do on
Yes.
in a glass, if there's a crack and then we scratch in front, then it doesn't go
Yeah.
to space.
So I also have these images. Very interesting. I mean, you should be aware of the things in a practice, how it looks like in a how it looks like in a workshop, how it looks like on the ground when you need to do some action, and to, I mean, not put the life of passengers in a jeopardy. So this can help us, I mean, to predict when the length of the crack is critical, and then to do something much before the length of the crack becomes critical. Because if you're waiting for crack to become critical. Last example that I know that a plane crashed because of the crack was in 2003, I think, or 2002, 6 months after those twin towers in New York collapsed. Okay, one Airbus was flying from New York to, let's say, Philadelphia, and after takeoff, vertical tail dropped. Okay, and fell into the yard of some guy in New Jersey. Okay, what was the reason for that fatigue? And then they check in the records that critical part that was broken. So predicted life was 10,000 cycles, flight cycles. I mean, in aviation, one cycle is one flight. We called it ground, air, ground. So I have, I mean, takeoff, you have flight, and then you have landing. And it was supposed to be replaced after 10,000 cycles, according to manual. and it was 9.5 thousand cycles when they check in the records. So never do that. I mean, when it's very close to. So they said, okay, we have time. It's we still have 500 flights, but you know, the same type of the aircraft can fly. I mean, in Africa all the time, where temperature on the ground is, let's say, in the summer plus 50, and when you're on 10,000 meters, it's minus 50. So have temperature difference of 100 Celsius in 15, 20 minutes. Okay, and if you have I mean, flights from Norway to Sweden, when in a summer you have only 25 degrees in a summer. So do you understand? So these differences. What is my point? So the same type of aircraft can fly in Africa or in America or I mean, very close to North Pole, for example. So conditions are not the same. And you cannot predict for all these conditions. So this is why we divide by factor 3. So if I get 100,000 cycles, I would say replace this after 30,000. Do not wait 90, because you never know. I mean, don't forget that basically, fundamentally, fatigue is a statistical problem. Crack will occur, you know, sooner or later. It's a must. So better do some preventive things sooner than later. Okay, thank you for your attention. Now it's my duty and my honor to introduce Professor Sedmak, who finally arrived.
Hello, everybody. It's a pleasure to be here. It's very nice to see young people who wants to learn. And I'm sure you had very good, excellent presentation for case studies. Very unique experience, actually. So I will just add a few facts, some conclusions on a general level. Professor Grbovic made comments, some discussion and conclusion about each case study. I will make kind of a general conclusion and few comments, review paper. Basic topic and basic issue here was about XFEM. So extended finite element method applied after about 10 years of theoretical development back in 90s, and then built in Abacus about 10 more years afterwards. So we in Belgrade, thanks to Aleksandar Grbovic, we were one of the first to really use it extensively. I even dare to say that there is something like Belgrade School of Numerical Simulation of Fatigue Crack Growth. So you definitely had the best presenter for the topic, my younger colleague. So conclusions are based on these case studies, literature overview, and some other case studies that we didn't have time to present. But the major conclusion is that extended finite element method is a versatile tool for simulation of fatigue crack growth in a complex geometry. That's quite important because for simple geometries, you actually don't need finite element method. So providing with the classical finite element method, possibly together, the best option, this is the best option for precise and reliable fatigue life of a cracked component and structure. You could hear just a couple of minutes ago that there is quite a confidence now in these results. Maybe decades ago, people would be afraid of this calculation, and probably most of you wouldn't board the airplane. A couple of decades ago, if somebody told you, I have calculated that, don't worry. But nowadays, this is really reliable thanks to these very, very sophisticated and versatile numerical methods. So it's not only XFEM, of course, although for some reasons, it was first extended finite element method and then classical finite element method to be applied for fatigue crack growth simulation. So let's focus on the second conclusion. XFEM is now in kind of a mature state. We know really a lot about it, but still remaining issues like meshing and location of initial crack, number and type of elements are to be still considered. And of course, the most important, which we lack from time to time, is verification with experimental results. I remember this famous example of wing spar. That was quite interesting. Number of cycles that were obtained numerically were too close to be true. We were so much surprised with the number. That was phase one. Agreement was in between 2% or something like that. Then in the second phase, when we looked again, we saw that actually predicted crack growth path numerically was different from what happened in reality. And then we were disappointed. But then phase three, think about it again, we concluded it is a coincidental or statistical or whatever, a matter actually of material heterogeneity. However material is good or component is well made, it's still a bit heterogeneous. So where crack would grow in real material depends very much on material inclusions or any other defects, and it can change the path due to its microstructure or defects or heterogeneity. It was not focus of this presentation, but just think about welded joints, which are often in trouble because of fatigue crack growth. So verification by experimental results, it's something that we must do, and not only for simple cases, but also with complex geometries, we can learn a lot, as I just explained. In any case, to further investigate all these issues, another advice is to use both methods, extended finite element method and classical finite element method. Now, why? Certainly you explained that, but it's good to repeat, I guess. Classical finite element method was practically impossible to apply because of need for remeshing. But a couple of decades passed, and then automatic remeshing emerged with acronym, which is really a good one, SMART. And I don't dare to try to say what it means, but in any case, it is automatic remeshing as crack grows, so you don't need to do anything manually. Of course, it would be impossible after each crack step to change the mesh. That would last for 4 years. So once this was solved, once this SMART technique, which was introduced in ANSYS, was at our disposal, then we really can have three important tools, if possible experimental, and certainly it is possible to use both numerical techniques and then to compare results. And that's the best part, the best way to get reliable results. And this is why you can fly freely, don't worry. Finally, data science and machine learning, artificial intelligence in one word, that's another important issue. There is a really place for it in our calculations. Well, SMART is a bit artificial intelligence, kind of, just to mention. But what we really need it for is any process that is done by hand and it's a long one. For example, did you explain about C&M, how you determine the Paris coefficients in that okay, so you saw that, and maybe if Aleksandar didn't mention it, artificial intelligence can do it for us in probably just a couple of seconds. The most important is to have database to manipulate with data in a proper way. And of course, still, whenever you use artificial intelligence, also rely on your own intelligence. Don't trust just what you see on the screen. Always think if this is reasonable. If it is reasonable, probably it's also correct. So that's about the conclusions. And I may say that most of what was presented here you can find in the review paper that was published recently. I wrote it, and this is why I am the author. But really, to be honest, it's based on all these papers that were more or less written by Aleksandar Grbovic, or even his students are listed here. Well, we work together, but that those are his students. Solob, he is for this lug, connecting lug. Then Eldvaib, he was doing on this wing spar cross section. You can see him. That's all. These students are from Libya. And Sguire, he was in charge of these panels, finger panels. And then only this case study 4 with nozzles were done by our students from Serbia, Martina Balac. In all cases, Professor Grbovic was the advisor, and so all honors and glory goes to him. Thank you.